Hello, everyone. My name is Cadet Adam Hoxing, and I'm a rising senior at the United States Military Academy at West Point. Thank you for watching my presentation, which concerns the streamlining of experiment projections for the Resolute-B Incoherent scatter radar to increase accessibility of research surrounding space weather-driven global positioning system scintillations. Here's a quick agenda for this presentation. Key things to focus on during this presentation will be the background information, which will provide necessary context to the research, the methods, which will explain the research completed, and the summary of work and tangible results, which will show the research's relevance and utility to other researchers in the field. Individuals, governments, and economies around the world rely on GPS signals every day for accurate position, navigation, and timing data. However, especially at high latitudes, these signals can be degraded or completely disrupted by adverse ionospheric conditions. The most prevalent example of such adverse conditions are caused by ionospheric scintillations. Incoherent scatter radars, abbreviated to ISR, such as the Resolute Incoherent Scatter Radar, are excellent tools for studying specific ionospheric parameters of scintillations that surround the path of GPS signals and cause the aforementioned inaccuracies. My work is in support of a larger research project that is co-authored by my research advisor, Lieutenant Colonel Diana Laux, that is studying scintillation-based GPS inaccuracies using incoherent scatter radars around the world. That research has stated the need for on-demand conjunction analysis tools developed with SDK and MATLAB, and my work meets that need for the Resolute by Incoherent Scatter Radar. Now I'll give some quick background on incoherent scatter radars. Incoherent scatter radars, or ISRs, are remote sensing tools that use radio waves to collect data on various ionospheric parameters, including the density, temperature, and velocity of free electrons and ions. They do this by emitting radio waves into the ionosphere, where they are absorbed by free electrons and ions. These particles then re-emit the radio waves back to the incoherent scatter radar. To produce the highest quality data, ISRs require certain environmental conditions at the time of data collection. The most important three of these conditions are the lunar phase, the interplanetary magnetic field polarity, and the temporal proximity to equinoxes or the winter solstice at the time of data collection. The ideal conditions for an ISR to collect data would be on the winter solstice with a new moon and a predominantly BZ south-oriented IMF polarity. This would simultaneously minimize extraneous signal noise while ensuring that the scintillations we are seeking to study are present. Now I'll give some quick background on the Resolute Incoherent Scatter Radar, also known as RISR. RISR is a twin-faced ISR located well above the Arctic Circle at over 74 degrees of latitude on Cornwallis Island in Canada. The north-facing radar, known as RISR-N, is funded and operated by the National Science Foundation, while the southern-facing radar, known as RISR-C, is funded and operated by the University of Calgary. You can see the two distinct faces of the radar in the picture in the lower left. RISR can be thought of as a radar of radars. Each of the two RISR faces contains 3,277 individual steerable radar beams that can independently study various ionospheric parameters. You can see a close-up of the RISR-C face in the bottom right photo, where you'll notice several of the individual radar beams. The fact that RISR provides several thousand individual radar beams makes it an especially great tool for studying ionospheric parameters that can cause inaccuracy in GPS signals. Investigators at RISR conduct this research by studying the ionospheric conditions around events that are called RISR GPS conjunctions. In short, conjunctions are any time a GPS satellite's orbit passes through one of RISR's many beams. The polar plot on this slide shows all the possible combinations of RISR GPS conjunctions that can happen each day. This plot is centered on the RISR site and combines the GPS orbit tracks, represented by the red dotted lines, and the RISR field of view, represented by the blue hexagonal fields, in order to illustrate where conjunctions can be found. Two other things to notice on this plot are the distinct circular area that has no GPS orbits and the canted nature of the RISR faces. That circular area is the result of the GPS constellation's design. GPS satellites have an inclination of 55 degrees and thus will not orbit above any latitude greater than that. This creates the circular hole free of GPS orbits that you see in the plot. This plot also shows how the RISR fields are canted off of true north and south azimuths. This is a purposeful design feature that allows both radar faces to take measurements in the ionosphere's polar cap. The polar cap is a hotspot for scintillations that cause GPS signal inaccuracies, and RISR's ability to study it is top-notch. This research seeks to design and implement an SDK scenario and accompanying MATLAB code to streamline the process of identifying and communicating upcoming RISR GPS conjunctions to RISR investigators in order to allow them to better understand the ionospheric conditions that cause scintillation-based GPS inaccuracies. To complete my research, I utilized 3 software packages: Systems Toolkit, also known as SDK, MATLAB, and Microsoft Excel. SDK allowed me to create a computer simulation of RISR's beams and the satellites of the GPS constellation so I could identify all potential RISR GPS conjunctions. MATLAB, a mathematical analysis tool, automated many of the necessary processes in SDK and also verified the legitimacy of any potential conjunctions that I found in SDK. Finally, I used Microsoft Excel to format and send my findings to the RISR investigators so they could execute experiments on found conjunctions. Now I'll talk about the methodology of my research. The first step in this work is to restrict the SDK scenario to dates on which RISR has experiment availability. This is an important step, as obviously it would make no sense to request operation of the radar on days in which it was conducting other experiments or down for maintenance. Next, I had to manually inspect the SDK scenario and record any potential RISR GPS conjunctions that were found. Of those possible conjunctions, I had to use MATLAB to filter out any instances of conjunctions without favorable radar geometry. Favorable radar geometry occurs when the cross pattern, which is shown in the bottom right corner of the slide, is present. That cross pattern is necessary to ensure that both the ionospheric data directly surrounding the GPS satellite signal, symbolized by the red point surrounded by the circle, and the ionospheric data in the neighborhood of the GPS satellite, symbolized by the 4 green dots surrounded by squares, are collected by the radar. Collecting both types of data yields a more complete and reliable data picture for the investigators. Next, I produced SDK access reports, which tell when and how long a specific RISR beam will be able to see a specific GPS satellite signal. The numerous produced SDK access reports were then compiled into a single Excel document and then sent to RISR researchers for experiment execution. To summarize the work completed, I have developed a methodology for identifying and verifying RISR GPS conjunctions using SDK and MATLAB. I've worked closely with RISR researchers so their specific needs and suggestions could be incorporated into the work, and ultimately I've been successful in sending RISR GPS conjunction times to enable further research into scintillation-produced GPS inaccuracies. Here are a list of the tangible results my work has produced thus far. Over 400 confirmed conjunctions have been sent to RISR investigators since January of 2020, and 70 of those have been successfully executed by the radar, and the data collected in those experiments are being processed and analyzed currently. You can visit the link on the slide to view all executed and planned operations at the RISR radars. Experiments executed on the conjunctions found in this methodology are labeled either GPS-N or GPS-C, depending on their radar of execution. Now I'll talk briefly about my next steps with this work. I've been successful in streamlining the conjunction identification and communication process for RISR, and there's now a lot of raw data that needs to be processed and visualized in order to actually produce valuable insights. A typical method to accomplish this is to use MATLAB. However, there are more novel and untested methods. One such method is to use ArcGIS Pro. I'm very familiar with this program thanks to my coursework as a geospatial information science major, and I'm confident that I could produce the same quality of result. I'd like to then compare the results from the two methods and see which produces more consistent and accurate results. The methodology I've developed can also be useful beyond what we've talked about today. With slight modifications, this work can be equally as useful to the ionospheric studies of other signal emitting satellites, as well as for amateur and professional satellite photographers. I'd like to extend my acknowledgement and thanks to a couple of people and organizations, namely Lieutenant Colonel Diana Laux, my research advisor, for all her help and support, Drs. Roger Varney and Rob Gillies, the principal investigators at RISR-N and RISR-C respectively, for executing the experiments I sent them and for their valuable input and feedback. Finally, I'd like to also thank the institutions that operate the two RISR phases, the United States' National Science Foundation and the University of Calgary. Finally, here are a list of my works cited for this research. This concludes my presentation today. Thanks so much for your time. And if you have any questions about my work, please feel free to email me at the address on the screen.